Welcome to this explainer. Today, we're jumping right into one of the most profound and fiercely debated questions in the entire history of science. Seriously, we're taking a front row seat to history's absolute greatest physics battle, a century-old war over the fundamental nature of reality itself. We're going to see how the greatest minds in history fought, experimented, and eventually completely changed our understanding of the universe.
Think about it for a second. You walk into a completely dark room, flick a switch, and boom, the space is instantly illuminated. But what is actually filling that room? What's bouncing off the walls, hitting your eyes, and allowing you to see? I mean, it seems like such a simple, everyday question, right? But the answer actually eluded humanity for centuries.
Okay, let's dive into this, because the scientific world was completely split down the middle into two contradictory camps. On one side, you had folks who thought light was a stream of tiny, microscopic particles, kind of like microscopic bullets shooting out of a light bulb. On the flip side, the other camp argued that light is a wave, spreading out through space, much like ripples in a pond. They couldn't possibly both be true at the same time. Or could they? To see how we actually cracked this mystery, we've got to look at the timeline of this epic intellectual rivalry. It's a total scientific roller coaster. We'll start back in 1704 with Isaac Newton's particle theory, then jump to the 1800s when Thomas Young seemingly proved light was a wave. We'll watch James Clerk Maxwell lock in that wave theory in the 1860s, only for Albert Einstein to come along in 1905 and completely flip the script back to particles.
All right, round one, the particle heavyweight.
Back in the 17th century, the absolute heavyweight champion of science was Sir Isaac Newton. I mean, when Newton spoke, the scientific community listened. In his famous 1704 book, Optics, he argued that light consists of these tiny little particles, which he called corpuscles. And his logic made total sense for everyday stuff. Why does light travel in straight lines? Because particles shoot straight. Why do we get sharp shadows? Well, because particles get blocked by objects, whereas a wave would just bend around them. And reflection, that's literally just a corpuscle bouncing off a mirror like a rubber ball hitting a wall. With Newton's massive authority backing it, this logical particle theory dominated physics for a solid century.
But science never stands still. Enter round two, the wave strikes back.
Challengers, like the Dutch scientist Christian Huygens, were brave enough to question Newton. He thought light was actually a wave traveling through an invisible medium called ether. Now, to get how this was proven, we first need to understand a concept called interference. Imagine dropping two pebbles into a totally still pond. Where the ripples overlap, they interact. If two peaks meet, they combine into a much larger wave. That's constructive interference. But if a peak meets a trough, they just cancel each other out. Destructive interference. This kind of behavior is entirely unique to waves.
Then, in 1801, Thomas Young pulled off his legendary double-slit experiment. He basically passed light through two narrow parallel slits and let it hit a screen. Now, if light were just particles, you totally expect to see just two bright lines on the screen, directly behind the slits. But nope, that's not what happened at all. The screen showed an interference pattern of alternating bright and dark bands. The light waves from the two slits were literally overlapping, reinforcing each other in the bright spots and canceling each other out in the dark ones. This brilliantly illustrated light behaving exactly like water waves, and it felt like a massive, fatal blow to Newton's particle theory.
Moving on to round three, Maxwell's electromagnetic victory.
The guy who seemingly delivered the final undeniable knockout punch for the wave camp was the great 19th century unifier James Clerk Maxwell. While he was working out his equations for electromagnetism, Maxwell actually mathematically calculated the speed that electromagnetic waves should travel through space. And the result? Roughly 300 million meters per second, which, amazingly, perfectly matched the known speed of light. That was definitely no coincidence. Maxwell figured out that light is actually an electromagnetic wave. It's just this beautiful, continuous dance of fluctuating electric and magnetic fields. And even better, it didn't need Huygens' imaginary ether to travel through. It could easily travel right through the pure vacuum of space. So by the 1870s, the battle was pretty much considered over. The scientific consensus was rock solid. Light was definitively a wave. Case closed, right? Well...
And now for round four, the photoelectric plot twist.
Now, what's really interesting here is the shocking experimental anomaly that literally broke classical physics. Just when science thought it had the whole thing figured out, this anomaly was accidentally stumbled upon in 1887 by the brilliant German physicist Heinrich Hertz. Hertz was actually just trying to prove Maxwell's electromagnetic waves existed, which, by the way, he did. But during his experiments, he noticed something incredibly bizarre happening with his metal electrodes whenever light shined on them.
Hertz found out that shining certain types of light, like high-frequency ultraviolet rays, onto a metal plate somehow violently ejected electrons right off the surface. This became famously known as the photoelectric effect. Now, at first glance, a wave sweeping over a beach and knocking loose a little bit of sand seems logical enough. But when physicists actually sat down and measured what was happening, the wave theory completely fell apart. Here is the paradox that left physicists completely baffled. If light is just a continuous wave, then a brighter, more intense wave should hit harder and impart more energy, right? But reality completely defied that. Making the light brighter only ejected more electrons, but they all have the exact same maximum energy. But the weirdest part was the red limit. If you shine low-frequency red light on that metal, absolutely nothing happens. 0 electrons. You could shine the brightest, most blinding red spotlight on it for a whole year, and still nothing. But the absolute second you shine even the dimmest little beam of high-frequency ultraviolet light, electrons pop off instantly. Classical wave theory had literally 0 explanation for this.
All right, round 5. Einstein returns to particles.
The physics world was totally stuck until 1905, when the ultimate scientific rebel stepped up. Albert Einstein did the unthinkable. He resurrected the particle theory. Einstein proposed that light doesn't actually deliver its energy as a smooth, continuous wave. Instead, it delivers energy in these discrete, indivisible little packets, or quanta. We later came to call these packets photons. This completely rewired how we visualize light. Instead of a continuous wave, you've got to imagine a stream of incredibly fast, completely massless bullets of energy. Einstein applied this photon concept perfectly to solve the photoelectric puzzle. Think of it like this. A single photon hits the metal and transfers all its energy to just a single electron. And the energy of that specific photon depends entirely on its frequency. High-frequency UV photons are like heady bowling balls. They pack enough of a punch to easily knock an electron free. But low-frequency red photons, they're more like ping-pong balls. They just don't have enough individual energy to do the job. And it doesn't matter if you fire a trillion red ping-pong balls at the metal, none of them individually has the energy to free an electron. Einstein's brilliant use of quanta brought particles right back to life. Which finally leads us to the quantum truce wave-particle duality. So, the crucial point is, who actually won? Did the particles win or did the waves win? Well, the result wasn't a clear victory for either side. It was actually a mind-bending compromise. If you set up an experiment to measure interference or diffraction, light will gladly show you its wave nature. But if you set up an experiment like the photoelectric effect, light will perfectly demonstrate its particle nature. Light isn't just a wave, and it isn't just a particle. It's this bizarre quantum entity that exhibits a dual personality, depending entirely on how we choose to measure it. Our classical everyday vocabulary just isn't equipped to describe the quantum world accurately.
And trust me, it gets even weirder. In 1924, a French physicist named Louis de Broglie came along and expanded this whole concept. He realized that nature loves symmetry, right? So if light, which we always thought was a wave, can suddenly act like a particle, then maybe matter, which we know for a fact are particles, can act like a wave. He proposed that every single particle, even the electrons inside your own body, has a wavelength. And incredibly, in 1927, this was confirmed experimentally when electrons were shown to diffract and interfere just like light. This bizarre dual nature isn't just a quirky rule for light, it's a fundamental property of literally all matter in the universe. Which brings us right back to where we started. I want you to look at the light in your room right now. What are you actually seeing? Are you being bathed in a continuous electromagnetic wave? Are you being bombarded by trillions of tiny massless photon particles? Or are you witnessing a profound quantum paradox unfolding in real time right before your eyes? This century-old war between particle and wave didn't end with a neat little winner. It ended by forcing us to expand our minds to understand the profound strangeness of the reality we live in. Thank you so much for joining me on this explainer. And remember, always keep questioning the universe around you.